Hello everybody. In this video we are going to be talking about Kirchhoff's voltage law, in which the idea is that around every single circuit there has a bunch of loops, such as this one, and the current around that loop will always create some voltage losses, and sometimes even entering batteries voltage gains. Regardless, it will always sum up to zero. So basically the sum of all voltages gained or lost inside any particular loop, such as this one, is going to equal to zero. So here's the basics of Kirchhoff's voltage law. As you enter a battery's negative terminal, my convention, obviously you can choose your own convention, but my convention is that you start off with negative 10, because you're entering a negative terminal, so it's going to be negative of whatever the battery's magnitude is. Then I add on some voltage lost due to this current going through the resistor. However, because this current is going in this direction, it wants to go down. However, as you can see, the blue current clearly wants to go up. Because we're viewing it through the lens of loop 1, we're viewing it as I1 to be positive, so we're hoping that I1 is correct. So we're going to write I1 minus I2 multiplied by 150, and there we go. Now we have the voltage lost from this resistor. In the context of L2, however, it's going to look a little bit different, and I'll also talk about that later. So basically now I1, for example, wants to go down, right? But I3, as you can see, clearly opposes that, wants to go up instead of down. So we're going to have to write I1, which we're assuming is the correct direction, minus I3, and we're going to multiply that by 20. All of this is to say this is equal to 0. Nice. Let's go ahead and talk about L2 now. L2 is going to be similar to L1, except for one small difference. You see, L1 and L2 have opposite directions, as I've assumed earlier. So let's talk about this one. This time we're looking at it through the lens of I2. So we're saying that anything that is up is positive and anything that is down is negative. So I2 wants to go up, but I1 wants to go down. So it's I2 minus I1 multiplied by 150. Then we're going to add on to the next term, which is just I2 multiplied by 220. And you see there's no opposing current here. It's kind of just monopolizing 220 alone. So therefore it's going to be I2 multiplied by 220. So here again, I2 is going in this direction. So it's kind of flowing from right to left. As you can see, I3 wants to go in this direction from left to right. So we're assuming that I2 is the positive direction, so anything that's going from right to left through this 220 ohm resistor is going to be correct. So it's going to be I2 minus I3 multiplied by 220. Alright, so we have one more resistor in this network, in this particular loop left, and that is going to be this resistor. Now, there's something weird going on over here, because as you may notice, there is a voltage controlled current source. Now there's a current source, which means that we're kind of given already what I4 is, right? You see this little direction of this current going around this loop? We're kind of given that. It's actually going to be the magnitude of V1 amperes. But in order to get V1 amperes, it's not that simple, because we need to take the voltage drop from this little resistor over here and then take it from 10, because we're going from 10 to some voltage drop here. This is our voltage drop to V1 and then ultimately to 0. So that's kind of like the order in which we're going in. So we need to find this voltage drop and subtract it. So essentially, how can we find the voltage drop? And this could be anything, right? V1 over here, this could be practically anything. It could be 5. If it was 5, well, I4 is quite literally just 5 amperes. But it's not, and in this case, we have to actually do a little bit more work, but it's not that much more work. And this is supposed to be a little bit of a challenge anyways, so we're going to go ahead and proceed. Now, we know that the starting voltage is 10 volts. That is given to us. It's over here, after all. And we also know that the current that goes through the resistor will induce a voltage drop. So that current that's going through here is what? It's just I2, right? Like I said, I2 is the only current that's monopolizing this resistor. So because of that, it's going to be I2 multiplied by 220 ohms. That is going to be the voltage drop across this resistor. But if we're subtracting that voltage drop from 10, then we're going to have whatever V1's voltage is. So if we're just going to go ahead and subtract this, just like that, therefore we now know with absolute certainty that this is going to be the value of I4, just like that. And it seems a lot more complicated, but it really isn't. This is literally I4. With that being said, let's go ahead and continue our loop 2 equation, which we never finished. We need to finish this last part. So loop 2 wants to go down, loop 4 wants to go up, so let's go ahead and write that down. So it's going to be I2 minus I4, but wait, I4 is actually this funny thing here, so we're going to actually have to substitute in that exact equation. I2 minus 10 minus I2 multiplied by 220, closing parenthesis, and another big closing parenthesis here. Anyways, we're going to now multiply this by 1000 ohms, which is actually this resistor where the battlefield between I2 and I4 happens. So that's going to be there, and all of this is to say is equal to 0. Wow, what a crazy equation. Again, let's go ahead and continue with loop 3. So loop 3 is going to look like this. Again, very similar to this giant scary parenthesis looking thing. It's going to exist because we have to deal with I4's current directions. Anyways, let's start off with nice and simple. I3 minus I1, because I3 and I1 is duking it out through the 20 ohm resistor, trying to see which one will win, and whichever wins gets to declare which direction the current goes in. Anyways, then we're going to have I3 minus I2. Again, I3 and I2 are fighting each other in the realm of 220 ohms, and one more resistor over here. I3 is duking it out with I4, so we're going to have I3 minus whatever this funny thing is. That's right, we're going to have 10 minus I2 multiplied by 220, closing parenthesis, closing parenthesis, closing parenthesis, and closing parenthesis. And where is this happening in? It's happening in the 220 ohm resistor. So there we go, is equal to 0. And just like that, now we have all the loop equations, and all we have to do is just go ahead and simplify it. Simple enough. And again, this is a giant system of linear equations. Highly recommend checking out the other video where I use a matrix, a coefficient augmented matrix, in order to solve for the reduced row echelon form for the system of linear equations. I will put that video in the description. Anyways, I will now hand this segment of the video to the animator. First, we copy the first equation, and we distribute out the 20 and 150 out onto the other terms, and reorganize the terms. Now, we can combine like terms and move that 10 onto the other side. Now that it's simplified, we put it back. Next, we copy the second equation. We're going to focus our efforts in primarily simplifying the nested parentheses thing here. Now we start off by distributing out the negative and combining like terms. I multiply out the 1000, and I remove the unnecessary parentheses. I now distribute out the 220, and I distribute out the 150, and I reorder the equation a little bit so that later on I can go ahead and combine like terms, like so. Now I move that 10,000 onto the other side and put the equation back now that it's simplified. We copy the third equation, and we're going to do the same thing here, simplifying that nasty nested parentheses thing. We start off by distributing out the negative, then distributing out the 220, then I remove the parentheses, and we're starting off from right to left. We distribute out the 220, followed by the 20. Once again, I reorder the equations, like so that I can combine like terms, like so. And then lastly, we move that 2,200 onto the other side. We put that equation back, and that's it. Okay, so over here, we have finished simplifying it. So we have the matrix, we take the reduced row echelon form, and now we have all the currents of the circuit's loops. So now, if you don't know how to go from here to here and from here to here, I highly recommend checking out my video on reduced row echelon formats using Gaussian elimination to go from here to here. And I'll put the link of that video in the description. So now let's go ahead and find the voltage drop across this 20 ohm resistor. So first we assume plus minus. So again, when we are plugging in a voltmeter, you'll sometimes see that it looks something like this, where there's the voltmeter machine itself, a red wire, and sort of, well, I'll choose a gray wire, right, for ground. Now, we're essentially assuming that the red wire is going to be plugged in here and the gray wire is going to be plugged in here, and essentially it's asking us if it's going to be positive or negative. In this case, it's kind of trivial. We don't really need to take that into account too much. But what I'm going to do is I'm just going to leave it intact. And I'm going to say, okay, now typically a ball will roll from a higher part of a hill to a lower part of a hill, ultimately changing its altitude in the negative direction. Now, because of that, we're going to assume that the current that's flowing downwards, aka this is kind of like our representation of the current, is going to be considered positive. And anything that isn't is going to be considered negative. And you see the only currents, plural, flowing through this 20 ohm resistor is I1 and I3, so I1 minus I3. These are the currents, and we're going to multiply this by 20, so V is equal to IR. And when we multiply these two things together, we're going to get about 1.12 volts. And we can go ahead and verify this using a circuit simulator just by going over here. Now here is the circuit simulator. I go ahead and run it. And now after running it, I can see that indeed V2 happens to be about 1.127 volts. So we did that math correctly. Let's go ahead and do some other voltage drops. Let's say the voltage drop across this resistor. Before I do that, I actually want to show you a kind of nifty trick that you can use on your calculator in order to get the results of this matrix. First, you want to go ahead and enter the matrix menu. Second, then press D. Then you want to go to Math, scroll down over here, and press 8. Then what we want to do is we want to go up and enter RREF of I, then press comma. Then we're going to type in the column, which is 4, because this is the first column, second column, third column, and fourth column. And then we're going to hit comma once more. And then we're going to go ahead and put it inside list 1. So second and press 1. Then closing parenthesis. Alright, now press enter. And just like that, now list 1 is populated with all of our entries over here. Let's go ahead and find the voltage drop across here. Let's go back to the drawing board first. Okay, so here we are. Let's go ahead and find the voltage drop in this direction. So again, we're assuming that this current is positive and anything else is negative. So what will that look like? Let's go ahead and rewrite that down. Well, the only current flowing in that direction, as far as I'm concerned, is going to be I3. I3 wants to go in this direction, right? You can just go ahead and follow the tip of the vector and you can see that I2 is actually going to be opposing it. So it's going to be I3 minus I2 as the true current, well, the true magnitude of current that's flowing through the 220 ohm resistor. V is equal to IR, so we can go ahead and find the voltage. And as it turns out, the answer to this is going to be somewhere around 0.614 volts. And we can go ahead and verify that by going back and plug in V3 and V2. So let's go ahead and see if that's correct. This is going to be 0.5 and then subtract from here. Okay, so let's go ahead and plug that in. V2 is considered to be plus, V3 is considered to be negative. So therefore, we're going to start off by subtracting 1.2715 and then minus 0.512254. As you can see, indeed, it is 0.614. Let's go ahead and verify our math using this new list that we have extracted this column. We're going to be considering that, again, just as a reminder, loop 3 to be positive minus loop 2. So let's go ahead and type that in. Loop 3 minus loop 2, and we're going to take all of this and multiply it by, that's right, 220. So as you can see, indeed, our rounding seems to be pretty similar, 0.61489, and then, of course, the rest of this is just truncated from the simulator, but you can see that it's pretty much the same. And therefore, we now know how to find the voltage drop across any resistor in the circuit simply by considering the current's direction. Speaking about current's directions, why don't we try and find currents through resistors? Now I'm going to go ahead and only do one of them because this is going to be a little bit complicated. My goal here is to find the current through resistor 6, because this is interesting, right? This resistor is kind of intersecting loop 3 and loop 4, and as we know, loop 4 kind of gave us a little bit of a headache. Let's go back to the drawing board. Okay, so here we are in the drawing board, and as you can see, loop 4 indeed did give us a few problems over here. We had to define loop 4 using our own equation, because we said that loop 4 is essentially the voltage drop across this 220 ohm resistor. Speaking of which, that should be I2 times 220, because I2 is the only current going through this resistor, thus that is the only current that is inducing a voltage loss through that resistor. Regardless, that's how we got this part of the equation. So now, with that in mind, how can we find what the value of the current through this resistor is? Suppose that I said, okay, I want to find the current in this direction. We don't really need to consider signs at this point. Okay, well, let's go ahead and think this through, right? Since I3 is going in this direction, is I3 considered to be positive or negative? Well, clearly it's opposing our measured direction, so it's negative. What about I4? Well, I4 seems to be supporting this direction, so it's going to be positive. But wait, we don't have an I4 in our matrix, so what do? Of course, we just plug this in, since we do know what I2 is after all. So let's go ahead and plug this in. Now, if we plug this into the calculator, let's see what we get. And let's see if this matches what the circuit simulator has to say. So here we are in the calculator. It's going to be 10 minus 220 I2. So that's going to be the voltage loss, right? And we want to know that since we are considering this to be in the positive direction, we now have to subtract loop 3, which was in the negative direction. So let's go ahead and subtract that. So again, all this is going to be subtracted by current 3. Okay, so we get 0.0023 something. Let's see, that was current through R6, and the current through R6, as you can see, indeed is negative 0.00232 something here, and as you can see, that is agreeing with what we got from the calculator. So there we go. Now we know how to find the current through any resistor in the circuit, as well as voltage drops across any resistor in the circuit using mesh analysis. Alright, so I hope that this video helped, and if you learned something new, please leave a like and comment, and I will see you in the next video, whenever that's going to be. See you next time.